2 pair, 3 sixes. Sorry fellas, I got nothing. Nothing? What do you mean nothing? Like nothing at all? No, nothing wins. It's a super rare hand. I mean, it's like a shiny Pokemon. Wait, you're saying you don't have anything? Guys, I promise nothing beats 3 of a kind. Let me explain. Hi guys, it's Lee Creighton. I'm kind of a math teacher. Let's talk about how we're going to rank hands in dice poker. So let's look at dice poker. How do you play? You take 5 dice and you roll them and you see what hand you can make from your roll. Here I've got a full house, 2 3s and 3 2s. Do it again. See what hand I can build. Here I've got a pair. One more roll. I've got 2 pair. So how do we determine which hand wins? Well, in poker, that's done by looking at which is the rarer hand. A straight is much rarer than 2 pair. So a straight beats 2 pair in the game. So in dice poker, we're going to see which hands are rarer than which other hands and build a table to show which hands win. To analyze the hands, I've made this chart listing out all of the possible combinations for 5 dice. You can get 5 of a kind, 4 of a kind, full house, straight, 3 of a kind, 2 pair, 1 pair, nothing. And I've written these in the order that they appear in regular poker. Now, 5 of a kind is possible in regular poker. I mean, I could have a wild card. This would be a 5 of a kind hand, and it's of course the most rare. So how am I going to write in this chart the 5 dice for each hand? Well, I'm going to use letters. You often use letters when you're studying combinations. You look at words and see the ways you can rearrange them. I'm going to approach this the same way. So 5 of a kind is going to be identical dice. That's 5 A's, 5 of a kind. 4 of a kind, I'm going to have 4 A's and a B. Full house, 3 A's and 2 B's. I'm going to skip straight for the moment. We'll come back to that. 3 of a kind is 3 A's, a B, and a C. Notice that if I were to have that C identical to the B, this wouldn't be 3 of a kind. This would be full house. So this does represent 3 of a kind. All right, 2 pair, 2 A's, 2 B's, and a C. 1 pair would be 2 A's and a B, C, D. And nothing, I'm gonna hold off again, just like straight, and show you a method at the end. So now I need to figure out how many ways I can arrange each one of these hands, because swapping dice, if I have this hand, I can put them in any order and it's the same hand. So I need to count arrangements of each one of these. And if you remember from your, advanced math class, when you've got repeated letters, like the word Panama, well, there's 1, 2, 3, 4, 5, 6 letters there. So there are 6 factorial ways of arranging them. But I've got 3 A's that repeat. So how many ways are there of arranging those 3 A's? Well, there's 3 factorial ways of arranging them. And I have to divide by that 3 factorial so that I don't overcount them. There's not actually 6 factorial ways of doing this because the 3 A's are indistinguishable. So let's go back to our chart. For 4 of a kind, for example, I've got a 5-letter word, so there's 5 factorial ways of arranging them. But 4 of the A's can be rearranged amongst themselves and get the same hand. So I need to divide by 4 factorial to get the actual number. In 5 of a kind, I have 5 factorial ways of arranging it, but all 5 are the same. So we can quickly fill in this column for all of these hands. 5-letter word here, but I've got 3 repeated A's and 2 repeated B's. In 3 of a kind, I've got similarly 5 factorial different ways, but I've got 3 factorial divisions so that I can take care of the 3 A's. With 2 pairs, still 5 factorial ways of arranging the letters, I've got two A's and two B's, each of which can be arranged. So I divide by 2 factorial both times. And finally, with one pair, I've got 5 factorial ways of arranging it, but I've got 2 A's that can be swapped because they're indistinguishable. Now that I've done this, I'm going to get my calculator out and figure out what each of these numbers is and fill in the rest of the column. So now that I've figured out how many ways I can arrange the dice, it's time to assign values to the faces of the dice. For example, 5 of a kind, it's 5 what? Well, 5 sixes, 5 fives, something like that. So I've got some tiles here that represent the faces of this die. Now, notice I'm not rolling the die around to demonstrate this. I think that's actually a little confusing for students. They need to choose from a set of 6 things, happen to be sides of a die, but I find it better if I choose from 6 actual things. So for 5 of a kind, how many ways are there of doing this? I want to choose one value, the value for A, and it's all A's. Choose one value for the 5 of a kind. How many ways to do that? Well, I think it's pretty obvious. There are 6 choices here to have your 5 of a kind. 6 fours, 6 sixes, whatever it is. There's a mathy way of writing this. To say I have 6 things and I want to choose one of them, I write it like this. This is called binomial notation. It's called combinations notation. Doesn't matter. Your calculator might have a button that says C, 6, choose 1. Either way, you're going to get a number for how many ways I can choose one thing from a set of 6. Similarly, for 4 of a kind, I'm choosing 2 things. I've got 4 A's and a B. So I need to choose 2 values out of this set of 6 to assign to my 4 of a kind. So for example, I might have 4 fours and a 3. Or I might have 4 ones and a 2. How many ways are there of doing that? Well, it's the same notation. It's going to be 6 choose 2, or big C, 6 choose 1. All this comes out of your calculator. What am I choosing for a full house? Well, I'm choosing 2 values, A and B. I might have 3 threes and 2 sixes. Point is, I'm only picking 2 values. Because there's an A and a B, I need to choose 2 things from a set of 6. For 3 of a kind, I'm choosing 3 things. I'm picking the thing that I'm going to have 3 of, plus the other 2 values. So how many ways are there of choosing 3 things from a set of 6? Well, that's going to be 6 choose 3. For 2 pairs, I'm picking an A, a B, and a C. My first pair, my second pair, and the singleton here. So I'm picking 3 things. Again, that's going to be 6 choose 3 ways of doing this. And finally, for 1 pair, so I'm choosing 6 choose 4. I'm going to get my calculator out and fill in the values for this table. So far we have figured out how many ways there are to arrange each hand. I've got 3 of a kind up here as an example. You know, we could have this 3 of a kind arranged in any way, and we have counted those arrangements, right? We have also decided how many different ways there are to assign faces to these dice. I can choose 3 things from my set of 6. I might get 3 fives, a 2, and a 1, or I might get 3 threes, a 6, and a 5. Once we've chosen them, that was our second count. Once we've chosen the values for the faces, we need to know how many different ways are there to arrange them. So, for example, in what I've just shown you, we might say that the A is the 6, the B is the 3, and the C is the 1. That means I've got 3 sixes, a 3, and a 1. All right. How many ways are there to arrange these faces? 3 factorial, right? I've got 3 things that can take any arrangement. There must be 3 factorial ways of doing it. Not exactly true, and let me show you why. Suppose I've got A is equal to 6, B is equal to 3, and C is equal to 1. So I've got 3 sixes and a 3 and a 1. Now, when we counted these, we said there's 3 factorial ways of arranging them. We're assuming that a 6 1 3 is different from a 6 3 1. we are assuming that order kind of matters. A 6, 1, and a 3 is different from a 1, 6, and a 3 is different from a 3, 6, and a 1. Look what happens when we actually roll these as dice. If my A is 6, and my B is 3, and my C is 1, that means I've got 3 6s and a 3 and a 1. Well, what happens if I take a distinct arrangement, 6, 1, and 3? What hand do I have? I've got the same hand. I've got 3 6s, a 3, and a 1. In other words, it doesn't really matter for these singletons what order they go in. So if I simply say there are 3 factorial ways of assigning these dice, I'm overcounting because some of those arrangements give me the same hand. Let me give you a longer example, and I think what I'm showing you will make more sense. So let's say we were playing a kind of strange 11 dice poker hand. Why not? So this is a possible hand that you could get, and we would be able to count how many ways to arrange these A, B, C, D, E, F letters, right? That's what our purple column was. We would also be able to figure out how many ways to pull however many faces I need. That's our green column. In this case, there happens to be 6 different letters, A, B, C, D, E, F. So in each case, we're going to choose all 6 dice. So now I have to figure out how to assign these dice to each of the letters to see what my hand is going to be. For example, let's just pick something random here and say that A is 5, B is 6, C is 1, D is 4, E is 2, and F is 3. So what do I have with this assignment? I've got 3 5s, 2 6s, 3 1s, a 4, a 2, and a 3. And since we're playing poker, we've got 2 3-of-a-kinds in here. Those 3-of-a-kinds are the A and the C. So I've got 3 5s and 3 1s. However, I could have easily made this assignment A1 and C5, 3 1s, 3 5s. I've got the same thing. Because I've got 2 3-of-a-kinds in my hand, it doesn't matter which one I pick for the 5 and for the 1. That is to say, when I'm counting the ways to assign the dice faces, assigning A5 and C1 is the same as assigning A1 and C5. Okay, what else do I have? Well, I've got a pair. So here I've got a pair of 6s. There's no other pair in here, so that is a unique thing. D, E, and F are singletons. They don't match with anything. And when I'm assigning the faces to the letters, this assignment of 4, 2, 3 is the same as assigning 4, 3, 2, which is the same as assigning 2, 3, 4. These all give us the same hand, right? Singletons that are 2, 3, and 4. So our question is, once we've selected the dice, how many ways are there to arrange these dice to each hand? What we have to consider is that there are 6 factorial ways of assigning these 6 things to these 6 letters, but some of those assignments give us duplicate hands, right? What I assign to A and to C can be switched, and the hand doesn't change. So in order to make sure I don't overcount, I have to divide by 2 factorial to take care of the triples. There's only one double, so I could divide by 1 factorial here, I guess. It doesn't change anything. I've also got 3 singletons, the D, E, and F. Whatever I assign to D, E, and F can be arranged in 3 factorial ways. So my point is, there's not simply 6 factorial ways of assigning this. There are overcounts when you do that. And in order to take that into account, I have to divide by the duplicate groups. I have groups of 3. I have groups of 1. So this takes care of groups of 3, this takes care of groups of 1, and this takes care of the single group of 2. So I've got a column that represents the number of ways I can arrange the dice. I've got a column that represents the number of ways I can choose faces, now I need a column to show how many ways I can assign those faces to the letters, knowing that some of them are going to give us repeat hands. So for example, for 5 of a kind, I've only got one letter, and it's only going to have one way of being arranged, so that's a 1. For 4 of a kind, I've got 2 letters, A and B. So I've got 2 factorial. None of them have repeat groupings. It's a 4 and a 1. So if you want to think about it as dividing by 2 1 factorials, you can. For a full house, again, I have 2 values, a triple and a double. So that's going to give me 2 factorial over 1, 1 is again 2. 3 of a kind, I've got 1 triple and 2 singletons. Here's the first time this is going to matter. I've got 3 ways to assign the numbers to the faces, but because I've got 2 singletons, I need a 2 factorial on the bottom to take care of the cases where that is double counted. You can think about having 1 factorial for the A's if you'd like. This is going to actually give you 3. Here I've got, for 2 pair, I've got 3 different things I'm choosing. So I'm choosing A, B, and C. But the A's and the B's are both pairs. So I need to divide by 2 factorial to take care of that, and 1 factorial to take care of the singleton. And that is 3. Finally, I've got 4 assignments that I possibly could make. However, the B, C, and D are all singletons, so that means that there's going to need to be a 3 factorial in the bottom to take care of the singletons, 1 factorial to take care of the 1 pair, and that is 4. Now I've got all the numbers I need to figure out how many possible 5 of a kinds, 4 of a kinds, full houses, and so on. I've got enough information to calculate how many possible ways there are to get each hand. All I need to do is multiply these numbers together. So for the first number is going to be 1 times 6 times 1, which is 6. Then 5 times 15 times 2 is 150. 15 times 10 times 2, that's 300. 20 times 20 times 3 is 1200. 30 times 20 times 3 is 1800. And 60 times 15 times 4 is 3600. This represents how many ways each hand can happen. There are 6 possible ways to get a 5 of a kind. There's 150 ways to get 4 of a kind, and so on. So I did promise to show you how to account for straights and for nothing hands. They're kind of special cases because I think there's only 2 ways of getting a straight, right? 1, 2, 3, 4, 5. I've got 5 dice. 1, 2, 3, 4, 5. Or 2, 3, 4, 5, 6. That's it. 2 ways. So let me write those down. I've got 1, 2, 3, 4, 5. And 2, 3, 4, 5, 6. There are only 2 ways of doing this. Down here, for nothing, well, how can I get nothing? I need to not have a straight and not have any pairs. So the dice have to be unique and they can't make a straight. So 1, 2, 3, 4, 6. 1, 2, 3, 5, 6. 1, 2, 4, 5, 6. Or 1, 3, 4, 5, 6. There's only 4 ways. Let me write those down. 1, 2, 3, 4, 6. 1, 2, 3, 5, 6. 1, 2, 3. 1, 2, 4, 5, 6. And 1, 3, 4, 5, 6. So that only gives me 4 things that I need to count. I am still arranging these in 5 different ways. So there's 5 factorial ways of arranging each hand, right? So 120 and 120. So when I'm doing my total count, how many possible straights are there? It's 120 times 2, which is 240, or 120 times 4, which is 480. Now that I know how many ways there are to get each hand, I could calculate a percentage, right? There's 7,776 possible hands, and I know how many of them are in each category. That means I could calculate a percentage. I'm going to write those percentages down so that you don't have to watch me calculate them, but they're all ratios. 6 divided by 7,776, 150 divided by 7,776, 30 divided by 7,776, and so on. So now we've got how rare each hand is, and we can rank them on that rarity. 5 of a kind is still quite rare, 0.08% of the time. Then comes 4 of a kind, 1.9%. Then comes straight. In regular poker, it's full house, but then comes straight, just barely. Then comes full house. So we've got 0.07, 1.9, 3, around 4. But next in rarity is nothing. Nothing is rarer than 3 of a kind, 2 pair, or 1 pair. So if we are saying that our hands are based on rarity, nothing beats 3 of a kind. Nothing beats 2 pair, and nothing beats 1 pair. Then to finish it out, 3 of a kind, 2 pair, and 1 pair are at the bottom. So when playing dice poker, nothing beats a lot of things. So to me, this is a kind of neat way of applying your combinations, your factorials, your counting theorems, to apply it to an actual problem, figuring out the hand structure of poker dice. But now that I've done it for you, how can you extend it into something you can do with your classes? When I was growing up, poker was 5-card draw. We used 5 dice. You could exchange, but it was a 5-card hand. These days, when you say poker, it tends to be hold'em. That is to say, you've got your dice, and there's dice in common for the table. So let's maybe extend our game just a little bit to where I've got the 5 dice that I roll, but then there's a dice in the middle that everybody can use in their hand. How does that change the structure of the game? Well, you just have to do a careful accounting of what the hands are going to be. You're going to have 6 dice, 5 yours and 1 theirs. How many different ways are there now of getting 5 of a kind when there are 6 dice? Well, I'm going to again represent this using letters. A, that's 5 of a kind, plus maybe a 6th dice that's the same. Or I could have the 5 dice, 5 of a kind, and a different dice. That is to say, all I need is 5 of the 6 of them to be 5 of a kind, and I'm going to represent that as either 6 A's, where they're all the same, or 5 A's and a B. 5 of them are the same, and there's 1 odd one. They are still 5 of a kind. We're not changing the number of hands. We're not creating new hands that you can have in this game. So I'm going to fill in this chart for rolling 6 dice so that you can see how many different ways there are of getting each hand. So here's the completed chart. Notice there's 2 ways to get 5 of a kind. There's 2 ways to get 4 of a kind. You can get 4 matching. The other 2 can be the same, or they can be different. Full house, there's also 2 ways. You can have, what you need is 3 and 2. So you can have 3 A's and 2 B's. That 6 dice can match the B's, or it cannot match the B's. So I've got 3 A's and 3 B's for the first case, 3 A's, 2 B's, and a C for the second case. Both of these are still full houses because there's a triple and a double. With 6 dice, there's only one way of getting a straight. 1, 2, 3, 4, 5, 6. That's all there is. There's only one way. 3 of a kind, I think there's only one way to get it. 3 A's and B, C, D. Because if any of these B, C, D's matched each other, they would be a hand up above. So if that B were in fact an A, I'd have 4 of a kind, and I've already taken care of that. If that C matched the B, that would be a full house, and I've already taken care of that. So there's only one way of getting 3 of a kind. Two ways of getting two pair. The important thing is that you've got A's and B's in pairs. You can have a third pair if you want, or two singletons, doesn't matter. Two ways of getting that, and I think only one way of getting one pair. Two A's and then four other things. If any of these things matched with the A's, I will have taken care of it above. Now, how many ways are there of getting nothing with 6 dice? I contend there isn't a way. In the cases we had before, such as 1, 2, 4, 5, 6, that for 5 dice, the 6th dice is either going to match one of these or it's going to be the missing thing, which would make it a straight. So there are no ways of getting nothing in the 6 dice variant. I'm not going to go through filling this whole chart out with you. We're going to have the same columns as we had before. We're going to have a column that represents the number of ways you can rearrange the letters. We're going to have a column to represent how many ways you can choose from 6 things, depending on how many of the 6 you need. And we're going to have a column that represents how many ways you can assign those faces to the letters, making sure that we don't double count. Let's do an example using, say, this bottom 2 pairs row. I've got a 6-letter word, and I need to know how many ways there are to arrange those 6 letters. Well, there are 6 factorial ways of representing 6 things, 6 factorial ways of rearranging 6 things, but I've got a repeated A and a repeated B, so I need to divide by 2 factorial times 2 factorial. That's arrangements of the dice. Now I need to know how many ways are there of choosing faces of the dice. That is, I need an A, a B, a C, and a D. I need to choose 4 things from a set of 6. So that's going to be 6 choose 4. That number will come out of my calculator. Finally, I need to assign these faces to these hands. So I've got 4 values that I'm assigning, A, B, C, and D. So there's 4 factorial ways of doing that, assigning values to A, B, C, and D. But I've got repeated doubles. So assigning something to A and something to B is the same as the reverse of that. So I have to divide by 2 factorial. I've also got repeated singletons, so I need to divide by another 2 factorial. I'll use my calculator to get the values for these answers. So we've got 180, 15, and 6. These numbers came from my calculator. I multiply them together. I find out that there are 16,200 different ways of getting this variant of 2 pairs. I can do the same thing for the rest of the chart and fill in how many different ways there are to get each of the other hands. Let me do that for you. So here's the completed chart. I know you can't read this thing. I do have a PDF with the case for 5 dice and the case for 6 dice all laid out. But I was able to get counts for each of these hands. Once I've got the counts, I can figure out the percentages, but let's remember that there's 2 5-of-a-kinds, there's 2 4-of-a-kinds, there are 2 full houses, 1 straight, 1 3-of-a-kind, 2 pairs, a single 1 pair, and we said there is no chance of getting nothing. So I'm going to add these up and divide by the total number, and I'll show you percentages. So we see that 5-of-a-kind is still quite rare. Next up in rarity is actually the straight. Next up is going to be 4-of-a-kind, and then 3-of-a-kind, and then a full house, then 1 pair, and then 2 pairs. So as you can see, when we add this 6 dice, the rarity of the hands really changes around. So I would say, if you've got an ambitious student, let them try this Hold'em variant where they have 1 dice in common, everybody else rolls 5. Alternatively, you could have a creative student do kind of the same analysis, except instead of having 2 different kinds of 5-of-a-kind, have the 6-of-a-kind and 5-of-a-kind be different. Also have the two different four of a kinds be different. They'd have to come up with new names. Have the two full houses be different. They could have a packed house and then a full house. Then they could see what ranking each one of those hands have. But you can get even more creative than that. Why stick with six-sided die? Here I've got eight-sided die. Now, what in your charts would change? What in this chart would change if you had eight-sided die? Well, you wouldn't be choosing from sets of 6, you'd be choosing from sets of 8. I'll let you figure out the rest of it. There's a PDF of my chart down in the description. Feel free to use it, and thanks for watching.